Good afternoon, good evening, everybody. My name is Monika Strangret. I'm the postdoc researcher in INAF Padova in National Institute of Astrophysics in Italy. And today I will tell you something about my work, which is focused on high-resolution transmission spectroscopic studies of the atmosphere of hot and ultra-hot Jupiters. So as we know, exoplanets are the planets which orbit stars different than Sun. And until today, we have 5,550 exoplanets discovered using different methodologies. But as I said, I am working on their atmosphere. So I will tell you something about the history. So the first exoplanetary atmosphere was detected in 2002 by David Charbonneau and his team when they detected the sodium doublet using Hubble Space Telescope in the atmosphere of HD 209458b. It's a quite famous exoplanet. A few years later, in 2002, Redfield detected also the sodium absorption in the HD 19733b using high-resolution spectrograph mounted on the Hobby Eberly telescope, so the ground-based telescope. And 2 years later, the Ignaz Snellen presented the work, which was also so focused on the high-resolution spectrograph from ground, but he applied a different method that is called cross-correlation method, which also changed astronomy. Exoplanetary atmospheric studies, and he detected CO in the atmosphere of HD 209458b. And as I said, we have 5,550 exoplanets discovered, but only 185 of them there are work that were focused on observation of their atmosphere. I'm not saying that in every planet we detected their atmosphere, but only it's less than 5% of the planets we use to look for their atmosphere. And as you can see from this plot, most of them, they are transiting planets, because I will show you some of the results and ideas why it's easier to detect the atmospheres of exoplanet using transit observation. Sorry. First, I said that I'm using the high-resolution spectrum. So when we observe the spectrum of planetary system, thanks to the different Doppler velocities of the planets which orbit its host stars, and the host star, and also the Earth, because we are observing from Earth, so we detect everything in our atmosphere. Thanks to those differences, we are able to study the atmospheres because we are able to distinguish those three signals. And I'm focusing on the transmission spectroscopy. So during the transit, when the planet goes in front of its hot star, and if the planet has the atmosphere, part of the starlight goes through the atmosphere of the planet and absorb the atoms and molecules which are in the atmosphere of this planet. And as this additional absorption moves in the radial velocity of the planet on its orbit. sorry. And to have this to detect the planet, we are using transmission spectroscopy. The problem is that we are observing whole system. So we need to apply a few things. First, the observation needs to be taken during whole transit, plus before and after transit. Why we need to do it? Because we have information how the stellar spectrum looks without the information of the atmosphere of the planet. Let's jump here. So this signal is the sodium doublet, and this is the sodium coming from the star. When we remove the star signal, which is average spectrum outside the transit, where we don't have the atmosphere of the planet, sometimes we detect some additional signal which is tilted, which means that it has different radial velocity. And when we move to the planetary rest frame, we always coadd all the spectrum that is inside the transit, and we detect the signal from the atmosphere. We need to coadd all the data because we are working on almost zero level, so we need to have reasonable signal to noise to be able to detect it. Other method, it's really similar. It's also transmission spectroscopy method, but it's focused on atoms and molecules, which has much more lines, especially like iron or water or CO. And in this method, we use the residuals, so the signal, the signal that we have minus star, and we cross-correlate those the models with the residuals. The important thing is to have precise, lineless and precise modeling. And so for this, we are using amazing code, Petit Trans, written by Paul Mollier. And thanks to this, we are able to create the synthetic models of the atmospheric spectrum for different temperature of the planets, from terrestrial to ultra-hot Jupiters. And here I would like you to focus on the left panel, which is the result from the cross-correlation. On y-axis, we have orbital phase. On x-axis, we have different radial velocity, depending how of the step that we are using cross-correlation. And as you can see here, this is the signal coming from the planet. And it's tilted because we are still in the stellar rest frame. And in this case, in this plot, the signal is injected to be able to see it by eye, because usually we are not able to see it by eye. We are later seeing when we coadd all the in-transit data. One other effect that it's really important to mention is the Rossiter-McLaughlin effect. We know that star rotates, and because we are observing spectrum, we are able to detect the changes when the planet crosses different limbs of different regions, different limbs of the star, because one part is blue shifted, one is red shifted, as you can see here. And this effect, thanks to study of this effect, we are able to tell something about geometry of the system. But unfortunately, this effect appears also only during the transit. So, and in many cases, this signal, especially the signal covers part of the regions where we expect the signal coming from the planet. But I will show you later why this effect is really important. And as my title said, I am interested in hot and ultra-hot Jupiters. What are those planets? Those planets are gas giant planets located close to their host star, and they have the Jupiter masses. You can see them, they are located more or less here. And because most of those planets shows that they are tidally locked, so one half of the planet is always facing the star, another not. So in consequences, there is a huge temperature difference, because they are close, and the one part is really always irradiated. The ultra Jupiters are like hot Jupiters, but their equilibrium temperature is larger than 2000 kelvins or 2200 kelvins, and the daylight could reach also 10,000 kelvins. And the huge difference is that majority of the molecules in the atmosphere are dissociated, and we detect the atoms in ionized state. And we also detect the winds because of the huge differences in the day side and night side of the planet. Also, difference between hot and ultra-hot Jupiters. For ultra-hot Jupiters in high resolution, we were never able to detect water. In low resolution, we are, but we are looking at different depth of the atmosphere. But for hot Jupiters, the water was detected in many planets. And what kind of First, what kind of spectrograph we need to use for this observation? Because I am working mostly in visible part of the spectrum, I'm using a telescope and that have visible range. So, for example, HARPS-N that is located at the Telescopio Nazionale Galileo in La Palma, in Canary Islands. Also, I'm using the telescope ESPRESSO spectrograph located on the VLT, Very Large Telescope in Chile. And also, sometimes I use also CARMENES in Carrel Alto and ESPRESSO in Arizona. There are also many spectrographs that are in the near infrared, but usually we have much more problems in this wavelength. So I just started my work with visible part. And here I will show you some results, some real data. One, it's my first work that was focused on the studies of the atmosphere of Mascara 2b, which is ultra-hot Jupiter, more than 2200 kelvins. And I was looking for the iron and ionized iron in its atmosphere using the cross-correlation method, because those two, iron and iron 2, they have hundreds of lines, so the cross-correlation method is the best for them. And as you can see here, it's the real signal coming from the atmosphere. And this, we use three nights of observation to be able to detect this signal, this really strong signal. And also we were able to detect the winds in the atmosphere, because the signal is, as you can see here, shows that the signal is a little bit blue shifted. Other work that I've done, it was transmission spectroscopy studies of 6 ultra Jupiter, which I always call problematic planets, because each of the planets shows some problems. And here I'm showing you the detection. We were able to detect the atmosphere only in one ultra-hot Jupiter, which was 189b. And using the cross-correlation method, we detected iron 2, and titanium. As you can see, maybe don't see, this is the signal coming from the atmosphere of the planet. This signal here, it's the Rossiter-McLaughlin effect. Fortunately, it's in a little bit different radio velocity. And we detected also the H-alpha, H-beta, and calcium-2 doublet. But why I said it was also the problematic planets. Here on the left-right, you can see Mascara 1b. And this black signal that you can see, it's not the signal coming from the atmosphere. This is the Rossiter-McLaughlin effect. And in this light tilted line, I'm showing where we expect the atmospheric signal. As you can see, it's almost impossible to look behind this effect, which covers the radio velocity that we expect the planetary signal. In this case, Mascara 1 is really, because it's really hot, ultra Jupiter, it's good to observe the day side. So we observe the planet on the other sides of the star. But again, as I said, there are different temperatures, so at the end, different chemistry in both sides of the planet. Here also is example of its planet, it's HAT-P57, and we have a Rossiter-McLaughlin effect here, and here also we have the pulsation of the star. And somewhere here we try to look for the atmosphere, so signal from the atmosphere of the planets. So it's also problematic. And the problem is that this Rossiter-McLaughlin effect, it appears almost all the time. Especially, it appears in the signals of the atoms that it's in the stellar spectrum. And the intrinsic thing is this is HD 209, and this planet is the planet where the sodium doublet was first detected. And as you can see here, this is a Rossiter-McLaughlin effect. So this paper by Nuria Casasay shows that we are not sure if this first detection was real first detection, because probably they detected a residual McLaughlin effect, which shows a little bit signal that looks like detection, but we are not able to go behind this effect. And as I told you before, we are able to also detect the velocities, and this example of what's 1-to-1 using ESPRESSO, which is amazing spectrograph that we were able to, in the mid-transit, our detected signal was clear, and when we observe only the one limb, we detected the strong winds. And with this plot, I will leave you, and this is the plot of all the on y-axis you have molecules and atoms, and on x-axis you have the equilibrium temperature of the planet, and as you can see, those are the different atmospheric detection of the exoplanet, and we still need to study it more. We need to find planets where we are able to detect more atmospheric signatures. Thank you very much.